Our final video for hyperbolas will be to complete an applied problem. Hyperbolas have real-world applications in astronomy, physics, engineering, and architecture. A good example is hyperbolic cooling towers. You can see some to the right on this slide, and this is what we see near power plants. We begin by finding the equation of a real-world hyperbola. The picture on the right in this slide shows a cooling tower. It is 179.6 meters tall, has a top diameter of 72 meters, and at their closest, the sides of the tower are 60 meters apart. So let's take a look at the diagram. Here's that overall height of 179.6. Here's the top diameter of 72. Here is the closest point of these two sides, here and here, 60 meters apart. And what we're looking at is shaped like this. That is the hyperbola we are looking for. So we'll find the equation to model the hyperbola for this cooling tower. We'll first assume the center of the hyperbola is the origin, the point 0, 0. And we'll use the standard form of a horizontal hyperbola centered at the origin. Now, a horizontal hyperbola, remember, looks something like this. And here's that center point. That's where the origin will be for this example. The equation for a horizontal hyperbola, a hyperbola with that transverse axis along the x-axis, is x squared over a squared minus y squared over b squared equals 1. Branches of the hyperbola will form the sides of our cooling tower. First step, find the value of a squared. And remember, the length of the transverse axis is 2 times a. The transverse axis in our picture is represented by where the sides of the tower are closest together. So let's look at the picture. We're going to draw in our xy coordinate plane, Cartesian coordinate plane. Here we go, x and y. This point where they intersect is 0, 0. That's the origin. It's the center of our hyperbola. These 2 points are 60 meters apart, given to us in the diagram, and we'll see the branches of the hyperbola. Well, that's not drawn great, but they will end up looking like this along the sides of the tower. So, taking 60 meters, 2a equals 60. We divide both sides here by 2. 2a divided by 2 gives me a. 60 divided by 2 gives me 30. Now we're looking for a squared, so a squared is 30 squared, and that comes out to 900. Feel free to pause the slides at any point, get that calculator out, and work through the math here. Second step, find the value of b squared. Remember, we're going to complete this equation, x squared over a squared minus y squared over b squared equals 1. We've already solved our a squared. That was 900 on the previous slide. And to find b squared, we'll substitute a known point into our equation for x and y. We'll use the top right corner of the tower right there. And notice that our y-axis bisects the tower. So we'll draw that in. This dotted line that they've shown, and then I've gone over in red, that's our y-axis. Now here's the x going right through that 60 meter point. My pictures aren't really straight, but we can imagine that they are. The intersection is the origin, and we know that our hyperbola has a point there and there. And we want to look at this point here in space. Because the y-axis bisects the tower, the x-coordinate may be represented by half the 72 meter distance at the top. 72 divided by 2 gives us 36. So let's look at this. We have 72 meters. We have this y-axis bisecting, perfectly cutting that in half. We divide 72 by 2, and this here is 36. So from this point all the way over to the point we're looking at is 36. Now the y-coordinate here is the distance from the origin to the top of the tower, which has been provided to us as 79.6 meters. So we go origin all the way to top of tower. We see right here that 79.6 meters on that distance over the 36 to that point that we're looking at. So our point here is 36, comma, 79.6. 79 along the y, 36 along the x, and there we have that point. Let's use the point. We have the equation x squared over a squared minus y squared over b squared equals to 1. We will rewrite that using algebra so that we have the thing we want, b squared, alone by itself on the right-hand side. And we see that in this second step, right here. Finally, we're going to plug in the coordinates we just found. Remember, we just found this point to be 36, comma, 79.6. That's our x is 36 and our y is 79.6. We plug them in, so y squared becomes 79.6 squared. X squared becomes 36 squared. Several slides ago we found that a squared was 900 and our minus 1 stays the same. Entering this into the calculator, being very careful where you put parentheses and the division sign. So I would enter this as, with parentheses, the 79.6 squared, and then a slash for division, another set of parentheses, 36 squared over 900, close the parentheses around that entire thing, and then hit subtract 1. And what you'll find is that b squared is equal to 14,400.3636. Finally, we can plug everything in and find the equation of this hyperbola. A squared was 900, b squared was 14,400.3636, and this is our final equation. And that's all there is to it.